Okay, let us continue to determine another parameter belong to the grand partition function, grand assembly, grand canonical assembly, so that we can completely understand that from the grand partition function, all thermodynamics, all macroscopic equation, parameter, quantities belong to the assembly can be readily obtained with a simple mathematical procedure. We have determined, we have derived the equation for the average number of particles inside the assembly and the average energy. Now let us consider another, let us determine the equations for another macroscopic property of the assembly. Now we start from the first law of thermodynamics. First law of thermodynamics. When the number of particles inside the assembly is constant, the first law of thermodynamics will read like this one: T ds minus P dv in case of reversible process. So the change of energy depends on the change of entropy and the change of the volume of the assembly. But in case of N is not constant, the change of energy is equal to T ds minus P dv, and this is mu dn. We have additional terms that account for the possible and particle change of particle number dn. Especially when the particle number is constant, dn is 0, then the equation becomes similar to the upper equation. Now let us consider the case when T, P, and mu are constants. Unchanged constants. When T, P, and mu constant, we can integrate both sides to have P equal to 2s minus P phi, and this is plus mu n. And we have defined that the Helmholtz free energy is defined as F equal to E minus Ts. This is minus Pv plus mu n. This is the Helmholtz free energy for assembly having not a constant number of particles when temperature, pressure, and the chemical potentials are constant. Now, let us look again at canonical assembly. Look again, because in case of grand canonical assembly, we nearly always consider the process of derivation in canonical assembly and then duplicate the processes in deriving the similar expression in the grand canonical assembly by making any appropriate adjustment. In grand canonical assembly, we have the probability of finding what the assembly with energy EI is equal to exponent minus EI of a KT, and this is the partition function of the canonical assembly. But in canonical assembly, we have the free energy equal to minus KT ln J. So from this one, we will you can prove easily this is equal to f of KT. This is taking the exponential on both sides, f of KT, and then this one. So the expression for the probability can be written as Helmholtz free energy minus EI and then of KT. This is for canonical assembly. Canonical assembly contains only has only different energy. The energy is not constant, but the number of particles is constant. Now we duplicate this equation for the case of grand canonical assembly. Grand canonical assembly, in which the number of particles and the energy are not constant. So for the case of grand canonical assembly, we write this one as Ni Ei, and this is equal to here independent of n. But in case of grand canonical assembly, this will depend on the number of particles. So here independent of the number of particles because number of particles is constant, but here depends on the number of particles because number of particles is not a constant. So we duplicate the equation, this expression in the case of grand canonical assembly. We adjust to consider the change of the number of particles, where F here independent of particle number becomes depends on the particle number. So after introducing that expression, we have shown that the Helmholtz energy is equal to minus PV plus mu n. So the depends on the Helmholtz energy on particle number is expressed in this one. Written is this expression. So for the case of grand canonical assembly, the Helmholtz energy that depends on the number of particles can be changed with this expression. So for the grand canonical assembly, the probability of finding assembly with a number of particles Ni and the energy Ei equals to exponent. We change this one with minus PV plus mu Ni, and then mu Ei over Kt. Okay? And if we sum all possibilities, we sum this one over Ni, this is P Ni Ei, and we sum this one Ni Ei exponents minus PV plus mu Ni minus Ei over Kt, and this is become 1. Okay? Because the summation of all probability over all possibility is become 1. So we have 1 equal to PV is independent of the index. We move outside over Kt, and then we leave only this one exponent minus Ni minus Ei over Kt. Okay. This is the expression for the grand canonical assembly. And look at this one. This is nothing but ZZ, grand canonical partition function, grand partition function. So we then obtain that exponent minus PV over Kp Z grand partition equal to 1, or exponent means by V over Kt if it plus equal to G grand. That means then PV over Kt equals to ln Z grand partition function. This is the equation of states for the grand canonical assembly. This is a equation of states for grand canonical assembly. PV over Kt equal to ln ZG. So we obtain the equation of state for the grand canonical assembly by simply taking natural logarithmic of the grand partition function. So we have obtained the average energy, the average number of particles, and the equation of state. For the case of ideal gas, this is must be equal to n. For ideal gas, must be equal to the average number of particles for ideal gas. So we have determined three quantities belong to the assembly, and another one is partition function, the Helmholtz energy. We then obtain here that after obtaining the equation of states, we can then obtain here the Helmholtz energy. If we look here that PV of a KT equal ln that means that PV is minus KT ln J plus minus KT dou of a dou mu ln ZG. This is average energy. So this is the average Helmholtz energy. So the Helmholtz energy, the average Helmholtz energy equal to KT. This is ln ZG plus mu dou of a dou mu ln ZG. We also see here that the quantity, thermodynamic quantity, can be obtained simply from the grain partition function. Another one is the entropy. Entropy is equal to F minus E. Entropy Ts equals to E minus F, or entropy is E minus F divided by T, because E has been determined depend on the grain partition function. F is this one, then the entropy is also or can be obtained simply from the grain partition function. So another one is enthalpy is energy plus PV. Energy has been obtained, has been derived. It depends on the grain partition function. PV is here, then the enthalpy can be obtained from the grain partition function. So we have shown here that all thermodynamics properties of the grain canonical assembly can be derived using simple mathematics from the grain partition function. So the grain partition function we have defined for the grain canonical assembly is correct, because from that function we will obtain all of the macroscopic properties of the assembly. Now the problem is how to calculate the grain partition function. We have defined the grain partition function, and we have shown that from that definition we can obtain all the thermodynamics properties of the assembly, but the main problem is how to determine the grain partition function. This is the most complicated problem in statistical mechanics, is to govern, to generate the expression for the partition function. For the canonical assembly, the most difficult portion is to determine the partition function of the assembly. And in case of a grain canonical assembly, the most difficult process is to derive, to get the expression for the grain partition function. In the next video, we will try to derive the expression for the grain partition function for classical particle and for quantum particle. Quantum particle is boson and fermion. What is the grain partition function for classical particle? What is the expression for the grain partition function for the boson? And what is the expression for the partition function for the fermion? If we have obtained that partition function, then then all thermodynamics behavior properties of the assembly can be simply obtained by just taking logarithmic, natural logarithmic of the grain partition function and perform partial derivation of the logarithmic, and that is the very simple mathematical procedure. Thank you.